Okay, next, in the next 30 minutes of time, Danny and me will be talking about some of our work on trying to use implicit representations in the field of robotic manipulation, of helping the robots make better physical interactions with the environments. And we'll discuss like what kind of scenarios we think implicit representation would be a good use, and discuss how it might be better or in compared to some other representation alternatives. So I will first start with this work called 3D neural scene representation for visual motor control. This is a joint work with Sean, Vincent, Phuket, Antonio at MIT. We humans have a very good understanding of the environment around us. For example, even if we're looking at this pouring environments from different camera perspectives, we all have a very good understanding of what's going on in this environment. What are some of the 3D structures of these objects within this thing? And based on this structural understanding and intuitive understanding of the 3D, we'll be able to do very actually challenging tasks. For example, pouring fluids into different containers of different amounts. And it's exactly this kind of intuitive models that observe the environment, predict how the environment will change if we apply our specific actions, and allow us to plan our behavior in order to achieve some specific goal. And in this work, we hope to modeling system of similar complexities. For example, we want to pouring fluids from the top container to the bottom. It actually involves complicated interaction between fluid and the container, between fluid and rigid objects. And specifically in this work, we want to ask the questions: can we learn representations directly from visual observations? And that is very good at capturing the 3D contents of the environments and can handle viewpoint variations. And then at the same time, the representation would be able to help us accomplish some downstream manipulation tasks. So very important question, what kind of scene representation we should use? You may think about maybe you could use pixels as a representation of the environment and predict pixel dynamics to predict how the pixel is going to change over time. This is what visual foresight is doing. But unfortunately, this may not be as applicable in our case because we really want to model in 3D, which typically this pixel dynamics only consider 2D dynamics. The other representation, we could use 3D key points as this work in key points into the futures. But however, key points are not as expressive in terms of describing objects with very high degrees of freedom, like fluids. Another representation could be, for example, using particles. But still, estimating the particle sets from visual observations can be very hard, which limited its use in these tasks. And the fourth type of representation would be latent vectors, which is what the current typical model-based reinforcement learning is considering. It typically maps observation into some latent vectors and predicts the evolution in this latent space to model its dynamics. And let's see how these latent vectors as a representation of the environment works in our scenario. Here's how it generally works. We have an encoder that maps observation Y as an image into some representation of the environment Z. And in order to ensure that Z encodes something non-trivial about the environments, there will be a decoder instantiated as a convolutional neural network to decode the visual observation from this latent representation. Prior work also considered to input to the decoder of viewpoints, trying to capture viewpoints variations. And here is how it will look like. On the left will be the ground truth visual observation. On the middle is how it will be decoded from this CNN decoder. If the camera viewpoint is within the training distribution, you can see actually the CNN decoder is actually doing a reasonable job. But as soon as the camera query viewpoint is outside the training distribution, the method is not doing very well when compared to the ground truth. And it's actually retrieved some nearest neighbor images from the training sets. So we all know convolutional neural network is very good at handling 2D images, but not very good at encoding 3D transformations or 3D invariances. But if we look closely at this decoding process, which is essentially a rendering process, they go from this latent representation Z into some visual observations. And we actually know a lot about rendering from graphics. So we're asking the question, are there any kind of structures we can add to this decoding function and allow us to learn representation Z that can have a very good 3D encodings of this environment? And in this work, we propose to use differentiable volume rendering, which is essentially the basics of neural radiance fields, which is actually very good at handling or providing spatial equivariances to the systems. And here is how it roughly works. Here is the thing with M2 model. We have a camera looking at the environment. And we can shoot rays starting from this camera center and going through a pixel of this image and pointing all the way through this environment. And we can sample points within this, along this ray. And for each point, it's essentially a position. And this position will go through multi-layer perceptions to predict the color and density for that specific locations. Then we'll do volume rendering along these lines to predict the colors of that specific pixel. We'll then compare the predicted color with the actual observations to compute the L2 loss and using that as a supervision to optimize the parameters in the nerve function. And typically this is done from multiple camera viewpoints, and all the points are actually the same for different camera viewpoints. So this provides very, very nice spatial equivalence. And here is how the results look like. Again, on the left is ground truth, on the middle is our baseline that uses convolutional neural network as a decoder. And here is our results. And you can see like when the camera viewpoint is within the training distribution, the rendering from our method is actually sharper and more consistent in the face of camera variations. The real difference shows when the camera viewpoint is outside the training distribution. Here the camera is closer, higher, and looking more downwards towards the environment. And here is our results. As you can see, our result matches the ground truth much better than the CNN decoder. And given this kind of encoding decoding model we learned from the data, we can actually also train a dynamics model over the latent space to predict the evolutions of the scene's dynamics. And here is our method's open loop future prediction. By open loop here, I mean that the inputs to our systems are only the initial visual observations and the subsequent action sequence. Our method has to hallucinate into the future and predict the interactions between the fluid and the container. Now here we are predicting 200 time steps into the future and still like producing very reasonable future results. Here's another example of shaking a box of fluids where we have a rigid cube floating on the surface. Our method will be able to capture the wave of the fluid as well as the movements of this little rigid cube. Here's another example of 3 cubes falling down and colliding with each other. And using this dynamics model, we can actually do model predictive control. Here we are using a sampling-based method to optimize the action sequence, and then using like feedback from the environment to give the model an opportunity to account for its modeling error. On the left is our goal image we aim to achieve, which is actually taken from a viewpoint that is outside the training distribution we use to train the dynamics model. On the middle is the control process, which is also the agent view. As you can see, it's very, very different from the goal image in terms of a camera viewpoints. And here is the control process. And here is actually the comparison in 3D space. On the middle is a controlling result from the goal image. On the right, we are showing the overlay between the control result and the targets shown in this 3D particle space. Our result is much better aligned with the targets when compared to the CNN decoder. Like here, we are really showing like the understanding of dynamics is important for this task. On the left is our target we aim to achieve. There's a little bit of fluids still remaining in the container. We first show like if we are using a PID controller, where we only want to match the pose of the containers, it won't be able to pour any fluid out. By learning the dynamics learned by our dynamics models, we'll be able to use MPC and to very reasonably accurately of pouring certain amount of fluids out and be able to also tilt the container back to match the targets. We also try to generalize to the real world. On the left is the setup we have that had 4 cameras looking at the environment. On the right is this data we captured. It is 4 RGBD cameras and it's synchronized and calibrated and record the environment at 15 Hertz. And on the right, we are using an April tag to track the movement of my hands to collect the action sequence. And here is actually the open loop prediction results using the learned model directly learned from the real data. Here we are actually pouring fluid from one container to the other. And our open loop prediction dynamics model can predict when the fluid will pour out of the top container. And the sequence goes by, it will also be able to predict as the top container becomes empty as we tilt it more. Okay, a little bit of recap here. The structure we are using here is a combination of latent space dynamics model plus this differentiable volume rendering benefited from neural implicit representation. It allows us to do very long horizon future prediction and novel view synthesis. And it can handle different initial configurations and different input action sequence. And that is the key to allow us to use this model for model predictive control. And can generalize, of course, different camera viewpoints, even viewpoints that are outside the training distribution. But there are limitations, because for this work, we are encoding everything into just one single latent vector, which is not able to handle systems that are compositional or more diversified, especially we have, for example, more containers, more cubes, more fluids. This one single latent vector models just won't be able to handle that. So Danny will talk about how we may be extending and add much more like advances on top of this framework to show like more structure in the system can actually allow this system to handle environments of more complexity. I'll switch to Danny. Thank you.
Okay, so in Dita's talk, we have seen that SOR nets have this great capability through the transformer architecture to generalize over different numbers of objects in the scene, especially to different numbers than they've been trained on. This is exactly something that we have seen with what Yunzhu showed, having difficulties if you want to generalize over environments where the numbers of objects are different to what you had in the training set. So this inspired this work, which we call Learning Multi-Object Dynamics with Compositional Neural Radiance Field, which is together with Jiao Wang, Yunzhu, Russ, and Marc. And the idea is basically, if you want to say it in one word, it's having the same architecture or a similar architecture, then a similar structure as Yunzhu uses, having an encoder and a decoder. But now, instead of representing the whole scene as one single latent vector, we represent each object as a separate latent vector. And, but then the details are actually quite different between these works. And now implicit representations will play a huge role and enable us to incorporate a lot of structural priors. And that is also the reason why why we wanted to make this workshop here, is to, so in robotics, very often priors are important for generalization, and through NeRF and implicit representations, I think we are able to incorporate these physical priors in our models in a very nice way, and we hope to discuss this with you and inspire research in this direction. So what we're doing, as I said, we make this framework compositional, and so the autoencoder framework becomes compositional, but then also the dynamics model becomes compositional as the dynamics in the latent space is being represented with the graph neural network. Very importantly here, the graph neural network has an adjacency matrix, and this adjacency matrix will be predicted from the neural radiance field itself. Okay, so to give you an overview, these are we start with observations of the scene from multiple views. And we also assume that we have masks of each object available, and these masks will enable the generalization over different numbers of objects. The encoder omega then now maps the initial observation of the scene to a set of latent vectors. And this encoder is trained with a decoder that is built from neural radiance field, but now this is a compositional neural radiance field that renders the set of latent vectors back to an image. And having this initial encoding of the scene, this compositional encoding of the scene, the graph neural network dynamics model now predicts the evolution of this latent space. And at any point in time, a forward predicted point in time, the scene can be reconstructed in 3D or rendered from arbitrary viewpoints with the NeRF decoder. Now I want to give some more details about this encoder structure. So for notation-wise, we assume that we have RGB images I from V many views, and we also assume that we have access to camera matrices. So these in this work we need calibrated cameras and masks of M many objects in the different views. So what you see here are just as an example of the real-world environment where we have 4 different input views of the scene. Okay, and the main idea of this implicit object encoder is to represent each object as a function over 3D space. So this function y here can be queried at a 3D location in space and outputs a feature. And this conditioned on the input observations. Now, given this function that you can query at a 3D location, we turn that into a latent vector through 3D convolutions. I will explain in a second why we are doing this, because this has some advantages. A little bit more in detail, we start with the world coordinate x, where we want to query a feature. We project it into the camera coordinates with the camera matrix, and then through bilinear interpolation, check what the RGB value of our input view is in this projected camera coordinate. And this interpolated RGB value together with an encoding of the projected coordinate is fused together to give us a feature from one view. So this now gives us a feature value for one input view. And we then combine different views together to one feature by summing all these features of the different views together if the projected 3D coordinate can be seen from that view. So what's cool about this structure is that it naturally handles occlusions, because only those features are summed up where there is actually information from one view, but it's also consistent from a 3D perspective due to this projection into the views. Okay, so this is how we build functional representations of objects. And to turn them now back into a latent vector, what we do is we have a workspace set, which is a voxel grid, so actually similar to what Dieter showed. And we query this function on this voxel grid, get a feature voxel out of it, and then apply a 3D convolutional network to get our latent vector for each object separately. Okay, so now that we are able to generate a set of latent vectors describing the scene, we render it back to an image with compositional neural radiance fields. And how does this work? So we now associate a neural radiance field with each object separately. So a neural radiance field outputs two things, namely a density and a color at a 3D location. And these two outputs are now conditioned on the latent vector corresponding to one of these objects. Now, as Yunzhu said, neural radiance fields are inspired from volume rendering, which makes a lot of sense from how light rays work. We can combine those separate nerves into one single one by just summing the densities up and weighting the color predictions. And using this, we are able to have as supervision signal just the full image, and that is being used as an image reconstruction loss through this compositional rendering. Okay, so for this is how we can generate a set of latent vectors from a scene, which is able to generalize over different numbers of objects. So now to the dynamics model. In principle, you can just think we just apply a vanilla graph neural network that predicts the evolution of the latent vectors given the current one. But very importantly, internally, a graph neural network relies on an adjacency matrix, which would indicate whether an object I and object J interact with each other. And maybe the uninformed choice would be to say, okay, we assume that this matrix is dense, and then let the neural network during training figure out whether objects actually interact with each other. What we propose here is to be a little bit more selective so this is an example scene where there are a bunch of objects, but those two objects, for example, cannot exert forces if there are no magnets or leaf blowers, which we have seen here on the conference. And then we thought that we might make the prediction problem for the neural network much easier if we incorporate this prior that no force exchange can happen if the geometries don't touch. And what we do is we take the neural radiance field density predictions and compute a collision integral of the two objects. So from the learned representation, we can actually compute a very reasonable and selective adjacency matrix, which incorporates this prior that objects can only exert forces onto each other if they touch. And that turned out to be very crucial in this work to achieve long horizon prediction and performance. And then one thing, I told you that this implicit object encoder was a functional representation at some point of an object. You could ask, why are you doing this? One reason for this is that so far I haven't told you how we incorporate actions into it. One way you can think of is, okay, I can just add an action as input to my graph neural network. But very often you can think, where does this action come from? In your training data, maybe if you want to scale to YouTube data where you maybe don't have actions available. And this, by having this implicit representation of the encoder, what we can do is we can apply rigid transformations to objects by transforming the input where this functional representation of an object is queried. So if we rigidly transform this voxel grid where this functional representation was queried by a rigid transformation, we get latent vectors that correspond to rigidly transformed objects. So this is important. This rigid transformation not only changes the appearance of the object, but it changes the latent vector. And this now allows us to, I explained here, so we have our initial latent vector. Now let's say we have control agency over one of the objects in the environment. We can apply a rigid transformation to one of these objects. And then this, which is the action, and then just ask the graph neural network to tell us how the system reacts to this rigid transformation in the scene. What's nice about this, in the training data, we don't need to store rigid transformations. We just need videos and masks of the objects. And then also during inference time, we can also change the object that is being articulated. So it's not set in stone that only one object can be the actor. Okay, now I want to show you some experimental results. So what you see here, this is a rendering of the initial scene from the neural radiance fields for some boxes here. And what you see now will be the open loop forward predictions over a very long horizon. And I mean, it's not 100% perfect, not by any means, but if you compare it to other methods that don't have this neural radiance field structure in it, the prediction very often get much more blurry, much quickly. And here, even after 100 time steps, these things still look like boxes. I mean, here it's kind of funny to see it changes color, but yeah. Okay, and one big reason for this is actually this adaptive way the adjacency matrix is estimated from the neural radiance field. As you can see here on the right, we have a dense adjacency matrix, and then on the left, it's our proposed framework. You can see there's much more drift in the system. And these are still boxes, yeah, but okay. And this is now a baseline, a CNN decoder baseline, the same one as Yunzhu was using, and this became blurry very quickly. Okay, now we also applied this to the real world, and it actually doesn't require so much time to train this, to collect data into maybe 4 or 8 hours of real world interactions. So this is now just, these are the observed views, and these are now just reconstructions from novel viewpoints. And here now, this is similar video as before. On the left, you see the real world. In the middle, you see the reconstruction if you had access to the images at every time step. And on the right, you see the reconstruction based on only the first observation and then forward predicting the dynamics. And you see that multiple objects interact here. And yeah, these objects are not 100% rigid. And this is now rendered from a novel viewpoint. So there was no camera view from above, but we can now look at how the scene looks from above. Sometimes it's not perfect, but qualitatively, in the sense of intuitive physics, I think it's very reasonable. Okay, and this whole framework makes no assumptions about rigidity of objects. Okay, it makes one assumption, namely that the acting object or that actions are rigid transformations. But apart from that, there's no prior or whatever, or no restriction to rigid objects. And therefore, we also tried whether it works with deformable objects. And this is now the same type of video. And actually, what was quite interesting, if you look at the quantitative results here in this scene, it was even better. So kind of the deformable object was, this scenario was easier for the method. Okay, and I think for the interest, 1 minute maybe. And we then also used this model to do planning and control. So this is an object rearrangement task. And why this? Maybe this task doesn't look challenging, but it is actually challenging if you have a learned dynamics model, because it's necessary to plan. It's not possible to do greedy planning here. If you do greedy planning, you might undo something, or you never achieve the goal. So you need a dynamics model that's capable of predicting long into the future without a lot of drift. And it also generalizes over different numbers of objects. Yeah. Here it's sometimes a little bit stupid, but able to recover. And what's cool is sometimes it uses, because it's planning in the joint space, it's moving multiple objects at the same time. Okay, I will skip that. So for conclusion, what we found is that neural radiance fields provide very strong supervision signal to train these embeddings. And estimating the adjacency matrix was a very important aspect here, and it was enabled due to this 3D prior that is in these neural radiance fields. And we achieved significantly better long-term prediction performance compared to multiple baselines. And I think one powerful insight is that latent representations learned with neural radiance fields seem to be very powerful. And I think also data has convinced us with great results that these learning embeddings with the right supervision can be a path forward in robotics. And I'm excited what we see in the future. Thank you.